All right, today we're jumping into a really cool mathematical puzzle. I want you to think of it like a detective story. You know, the clues are all equations, and the crime scene, well, it's this abstract space. And at the heart of it is a riddle that, I promise you, sounds like it completely breaks the rules of logic. So what is this mystery? Get this. Imagine you have a house, right? And you measure the size of 3 different rooms inside it. Then you add those 3 sizes together, and the total comes out to be twice the size of the entire house. How on earth can that be possible? It just doesn't make any sense, does it? Well, that's exactly the paradox we're gonna crack today. Okay, so before we start piecing together clues, every good detective needs to know the basics, right? We've got to meet our cast of characters and get familiar with the lingo of this particular mystery. Let's lay the groundwork by talking about spaces and dimensions. So first, we have what's called a linear space. We're just going to call it V. The easiest way to think about V is that it's the entire house. It's the whole universe where our mystery is taking place. Everything, and I mean everything we're about to talk about, happens right inside this house. And of course, inside our house V, we have rooms. In math speak, we call these subspaces, or U. That's all they are, just rooms inside the main house. The key thing to remember is that these rooms have to play by the same rules as the house itself. You can't have a room where gravity works sideways, right? Same idea here. Okay, so we have a house and we have rooms. But how do we talk about how big they are? Well, that's where this concept of dimension comes in. We'll just shorten it to dim. For our little detective story, you can just think of dimension as the size, the square footage of the house, or any of the rooms inside it. Simple as that. All right, now this is where it gets interesting. These rooms can interact with each other in a couple of important ways. First, you have the intersection. That's just the part they share. Think of it like a shared closet between 2 bedrooms, or the hallway they both open into. It's the overlap. Then you have the sum. This is the total area the 2 rooms cover together. It's like you knock down the wall between them. And notice, it's not just adding up their individual sizes, because you got to be careful not to count that shared overlapping part twice.
Okay, we've got our definitions down, we know the setting, it's time to open up the case file and see what clues we're working with.
So here are the clues left at the scene. We've got 2 of them. Clue number 1 tells us that room 1, combined with the shared part of room 2 and room 3, perfectly fills up the entire house. Now see that little plus sign in a circle? That's super important. It means this isn't just a casual combination, it's what's called a direct sum. Think of it like 2 puzzle pieces that fit together perfectly with absolutely no overlap at all. Then, clue number 2 tells us that if you combine room 2 and room 3, that's also enough to fill the whole house. And this is the central puzzle. This is what we have to prove. Given just those 2 little clues, we need to show that the size of room 1 plus the size of room 2 plus the size of room 3 all adds up to 2 times the size of the whole house. I mean, come on, that sounds completely bananas, right? But somehow, the logic is going to get us there. Let's see how. So, we've got the clues, and we've got the baffling puzzle. The question is, how do we connect them? Well, it turns out we have a kind of master key, a fundamental rule that unlocks how all these different room sizes are related. And here it is. This is our master key. It's called the dimension theorem, and it's our secret weapon. What it does is give us a perfect, reliable formula that links the size of any 2 rooms to the size of their shared space and the size of their combined space. This is the tool that's going to let us tie everything together. Okay, let's walk through the deduction here step by step. First, we take our first clue. Remember, it was that perfect, no overlap fit? That means the math is really easy. The size of the whole house is just the size of room 1 plus the size of that shared bit from the other 2 rooms. Simple enough. Now for step 2, we pull out our secret weapon, the dimension theorem. We take that size of the shared bit and we swap it out for the whole formula from the theorem. Okay, so now our equation is a little longer. For step 3, we use our second clue. We know that room 2 and room 3 combined make up the whole house, so we can just replace that part of the formula with the size of the house itself, dim V. And now look at what we've got. The final equation says the size of the house equals the size of all 3 rooms added together, minus the size of the house. Now that is a weird-looking statement, but trust me, we're just 1 step away.
And here's the final move. All we have to do is a tiny bit of algebra. We just add the size of the house, that dim V, to both sides of the equation, and boom, there it is. The size of room 1 plus room 2 plus room 3 equals 2 times the size of the entire house. The impossible has just become fact. The main mystery is officially solved.
This is something I just love about math. When you solve one problem, it's like you've forged a new tool. And that new tool is often exactly what you need to crack the next puzzle. So our investigation isn't quite done, but the heavy lifting is over. So let's not forget what we just accomplished. This equation we came up with. It's not a guess, it's not a theory, we have proven it. It's now a rock-solid piece of evidence, and we're going to use this very result to solve the second part of our mystery.
All right, so here's the second puzzle. Can we prove that room 3, combined with the shared part of rooms 1 and 2, also makes a perfect puzzle piece fit of the whole house? If you look closely, that looks an awful lot like one of the original clues we were given, just with the numbers shuffled around. Isn't that interesting?
We're going to use the exact same detective method here. So first, a little side work with our original clues shows that rooms 1 and 2 combined also cover the whole house. Okay, good to know. Then we look at the size of the thing we're trying to prove. You know, the size of room 3 plus the size of that shared bit between 1 and 2, and what do? We pull out our master key, the dimension theorem, one more time. And after we do the substitution, we get an expression that looks, well, it looks like the size of all 3 rooms added together minus the size of the house. Does that ring a bell? It should.
Because remember what we proved in the first part? We know for a fact that the sum of those 3 room sizes is exactly 2 times the size of the house. So our little formula becomes 2 times the house size minus 1 times the house size, which just leaves the size of the house, din V. We've just proved that the size of our new combination is exactly the same as the size of the entire house. And in this world of linear algebra, if a room inside a house has the same square footage as the house itself, well, it has to be the house. There's nowhere else to go. Case number 2, closed.
So, you know, the really cool thing here isn't just that we solved it. It's what the solution shows us. When you take a step back from all the pluses and minuses and just look at the big picture, something really elegant and beautiful emerges.
Just take a look at this. On the left, that's one of the clues we were handed at the very beginning. And on the right, that's what we just proved. Do you see it? It's this incredible symmetry. The numbers, the indices 1, 2, and 3, they've just been cycled around. The same relationship holds true, just with the roles of the rooms swapped. It's this beautiful hidden balance that was there all along. And really, that's the whole point of this journey. We started with what sounded like a complete paradox, right? 3 parts adding up to twice the whole. It's nonsense on the surface. But by just patiently following the rules of logic, one step at a time, we found that hiding behind that confusion was this perfectly balanced, elegant truth. And that's not just a math trick. That kind of thinking is what powers discovery in pretty much every field you can imagine. Kinda makes you wonder, doesn't it? I mean, this was just one little puzzle from one tiny corner of mathematics. What other incredible, hidden truths and things that sound totally impossible are just out there in the abstract world, waiting for someone to come along and start following the clues?